So the next person is Professor Jacques Slotine. He's famous for the nonlinear system and sliding mode control. Yeah. So when you are ready,
does the microphone work? Yeah.
Yes, please.
Yeah. So I'd like to thank the organizers for inviting me. It has been a very fun conference so far. And also so far, my only contribution to the conference has been to suggest to the organizer the @ sign in the title. So I'll try to do a little better now. So if you consider a passenger airplane, a commercial airplane, it's designed to be reliable at 10 to the minus 9, which means that there is only a chance of 1 in a billion that something goes wrong in the next hour. Okay? That's how the entire airplane is designed. That's how the control system is designed, everything. Okay? And so how would you like to board your airplane and the captain says, well, welcome aboard. You'll be glad to know that the controller of this aircraft was designed using the latest neural network techniques from DeepMind. And as a result, we have 96% chance to land in Amsterdam. Because that's pretty much where we are, right? So in a sense, you want to be able to do both. You want to be able to exploit what you can get from deep learning, but at the same time, you would like to have formal guarantee of what's happening, and you'd like to be able to push the envelope to get, reliability and so on. So of course, as we all know, a source of inspiration for learning is the brain, which has about 10 to 11 neurons and 10 to the 4 connections per neurons. So if you take these 10 to the 15 connections, it's a big number, and one way to see it is that if you imagine that from the time a baby is born to the time she goes to college, she has to create about 1 million new connections per second. Okay, per second, she has to create 1 million new connections. And, so it means it's very complicated dynamic systems with lots of feedback and so on. But the other important question is, how do you meaningfully create 1 million new numbers per second, on the basis of the information in the last second? So the other thing, of course, is the brain is dealing with desperately slow hardware, right? 10 million times slower, a neuron reacts 10 million times slower than the transistor. And still, we know we're near having a great robot basketball player, let alone a robot plumber. So for me, one of the key questions at the moment is, for robotics, I guess, is what happened to C-squared? So you have no idea what I'm talking about, but so C-squared, so we were all raised on the idea, which I think is correct, that the brain is the result of the progressive refinement of sensory motor control. Predators got better at being predators, and prey got better at escaping predators, okay? And the poster animal for this is something called the C-squirt. The C-squirt is a little, marine animal which which swims, most of its life, and at some point it fixates itself on a rock. At the point it fixates itself on the rock, it swallows its brain, its own brain, because it figures out, if it doesn't need to move anymore, it doesn't need a brain. So the brain has been very much the result of, the refinement of sensory motor control. And now we have this very strange thing where we have LLMs and so on. We used to think, well, you had the brain, and then you had humans, and then you had language, and so on. And now we have, very plausible language, definitely passing the Turing test and so on. Before motion, we can do all sorts of fun AI things, and we'll be able to do more and more, even mathematics and so on. But we haven't really solved the motion problem yet. And again, as I said, we neither have LeBron James or a great robot plumber. That might explain why perhaps so far these things are not so good at qualitative physics or common sense, because they never had to work hard on it, right? They never had to build from the real physics, you know. They were parachuted from, you know, reading millions of pages on the internet. So the tools we're playing with to try and understand these questions, you know, are the usual ones, the Lyapunov theory and so on. We're trying to get formal results. One we've been developing particularly with this absolutely brilliant student named Winnie Lohmiller since 1988 is what we call contraction theory, which kind of a, if you want, a more modern version of Lyapunov or a differential version of Lyapunov. And so when we developed this, you know, we were just saying, well, you know, Lyapunov theory is virtual physics, but it's mostly virtual mechanics, you know, and so could we think of virtual fluids? And so that's what, you know, how we came up with that. And so, you know, a system is contracting. If any two solutions converge exponentially, they could be overshoot and so on, but in the end, they converge exponentially. And the main result is this is true if the Jacobian of the system, in other words, the linearization of the system, is negative definite everywhere in some metric. So in other words, of course, it's not the linearization at the point, it's the linearization everywhere, and that's an if and only if condition, which means that if you use these techniques, you can use all what you know about matrices and so on rather effectively to solve completely nonlinear control problem. So I will skip the math because we don't have time, but one of the nice properties of a contracting system is that it has these aggregation properties. So if you have contracting building blocks, then you can use them as Lego block to recursively build very large contracting system without having to prove stability again, as long as you have the stability of the contraction of the individual blocks. And so very quickly, I don't have time for that, but things you may be familiar with, like sliding variables, you know, composite variables can be viewed as creating hierarchies of contracting systems. Control primitives, if you have a bunch of dynamics, and if you have a dynamical system and you have a number of control laws, each of which makes the closed loop system contracting in a common metric, of course they will tend to different things, they'll do different things, but they'll be contracting, then automatically any convex combination of these control primitives will also make the system contracting. Okay? So it says, you know, you can plug and play very easily, and it's a very simple tool if you want to think of stability of systems with control primitives. Another simple example is, you know, primal dual optimization, as in constraint optimization and so on, and it's very easy to analyze primal dual optimization, and you can do it with a metric. Okay, so. So if you want to just getting back to that a second, right, it says that Jacobian is negative definite in some metric. What's a metric? It's a differential coordinate transformation, okay? So it's something which is not necessarily integrable, but it's a differential coordinate transformation. And so basically it's Riemann coming to the rescue of Lyapunov, right? It's a way of building Lyapunov-like functions by using very, very simple differential geometry. Okay. So also, if you have a contracting system which is driven by a periodic input, the system could be completely nonlinear, but is driven by a periodic input, then the state of the system will automatically converge to a state of the same period. So that's the basic, so one way to summarize this is this, with if you have a metric of the form theta transpose theta, where theta is a function of the state and time, what you want is this so-called generalized Jacobian or Riemannian Jacobian to be negative definite, or equivalently, you want this equation to be verified for some positive alpha. And then this means that the geodesic length, the Riemannian length between any 2 points decreases exponentially with this rate alpha. Now, we can apply this to, for instance, to just a gradient system or even a natural gradient system with its own metric, a different one, right? So if you have a gradient system, it converges exponentially to a unique global minimum, not, of course, if the function is convex, but simply if it's contracting in some metric, right? If the dynamics is contracting in some metric, then automatically the system converges to a global minimum. More subtly, suppose that alpha equals 0. So in other words, it's not that you have distances that shrink exponentially, you have distances that don't increase with respect to some metric, okay? So alpha equals 0. Then you can show that if you have a gradient or a natural gradient, then automatically this system will converge to a global minimum of the cost. That this global minimum in general will not be unique. And that all global minima will be path connected. In other words, you have a topology very similar to what you find in deep learning, where you have lots of good solutions, they're all connected by good solutions. And for this, you only need the semi-contraction of the system with respect to some metrics. So in a sense, you have all these algorithms, transformers, and so on. And they have, in a sense, they are very simple. They would be almost comical if they didn't work so well, right? And the reason they work is that if you have tons of data and over-parameterized or highly parameterized gradient descent, then you actually fit a function. And this is a kind of a way of seeing this. It's saying, okay, if you have a very large dimensional system, the metric varies as n squared. So whether the system is semi-contracting with respect to some metric becomes more and more plausible as n increases, and you can be more precise than that. Okay. So I don't have much time left, so I'll just say that you can talk about. Give me a few more minutes. We're on at 15, okay. But still. So you can talk about gradient, you can talk about adaptation of a system, and standard adaptation, Slotine and Lee algorithms and so on, they can all be rewritten as gradient descent in the parameters, but not on the Lyapunov-like function, V0, which corresponds to the nominal contracting system, but to the derivative of the Lyapunov function. That's what you have in adaptive control. You learn just enough to get the task done because what you learn depends on the task. You can show that if you replace this gain matrix by the Hessian of some cost function on the parameters, then automatically if you are over-parameterized, the system will automatically tend towards the set of parameters that also minimize this cost function while also doing its usual adaptive thing, right? So for instance, if you pick a cost function which is an L1 norm, then basically you're going to sparsify the parameters which give you a specific adaptive control performance. And one of the applications of that is multiple models. The fact that you could have, especially in contact and contact control and so on, you may not know exactly what the physical model of the system out there is, but you may have lots of hypotheses, and you can online, this adaptive thing is online and fast, play with, basically pick the right model and the parameters. Okay, so skip that, and you can apply this to optimal policies as well, right? If you have a Lyapunov-like or a contracting analysis for your adaptive controller, for your optimization, then you can automatically make it adaptive. Last point, we keep hearing, and people in neuroscience department and so on, get a lot of money from this, and I'm partly the neuroscience department too, on the notion of the fact that, AI was informed by neuroscience. And yes, it's true, except AI has not been informed by any single result in neuroscience of the last 50 years. Okay, there's no result in neuroscience in the last 50 years which made it into AI. Okay, or there are very small details. Okay, everything else, neural networks, even dropout, and so on. These are ideas which are more than 50 years old. So the other thing is that that's my last slide. Keep talking about neuroscience. But actually in the brains, there's other things than neurons. In particular, there's cells, glial cells, which are about as many as neurons, which are called astrocytes. And these astrocytes are, as the name indicates, are star-shaped cells, and they have interesting properties that a single astrocyte can connect to hundreds of thousands of synapses, okay? So originally, people thought that this was just for cleaning, cleaning chemicals after action potentials and so on. But of course, there's no reason that evolution didn't realize that, having all these synapses connected by this extra network has really interesting computational properties, okay, computational potential, okay? So we built a model of that, so X would be membrane potential, S would be the synapse strength, and this is the processes of the astrocytes. And what you can show is, first of all, you can show this can all be done stably and so on, but you can show that depending on how you choose the process of the astrocytes, you get very different computational capability. If you use the process of the astrocytes to all be the same, so basically you diffuse between synapses, then you get exactly a transformer, right? So on the one hand, if it is the tensor which connects the synapses is very, very simple, you get the transformer, you get transformer attention. On the other hand, if it's extremely precise, you get dense associative memories. In other words, what's called modern Hopfield networks, okay. So very simple choice of the coupling between in the astrocytes you get transformers. Very detailed choice between the astrocytes, you get dense associative memories. All of these extremes are known. But this says there's an entire continuum between those yet to be explored from a machine learning point of view. And so I'll stop here.
Thank you very much. So as we have no time, so I'm sorry, I cannot accept any questions. But during the coffee break, ask him about his talk. Thank you very much. Big hands again.